So welcome back. We are now in bilinear interpolation. So for bilinear interpolation, the previous methods we've been considering, both for the Lagrange and the Newton's divided difference, it's in 1D. Simply put, we are just giving the value of f of So simply put, we are just giving the value of f of x. So the previous method was one-dimensional. Control Z. So we are just giving f of x. So for bilinear, we are giving is in 2 dimensions now. And we want to, given the known points, so given xi and yi, in the previous examples we've been doing, is just f of x. So it's just 1D. So bilinear is 2D. So when you are giving values that involve 2 dimensions, so here is x1, here is x2, here is y2, when my cursor is y2, and here is y1. So you are given this point, and you are given the value of the function at this point. So this is the f of x1, y2. This is the value of the function here. Then this is the value of the function f of x1, y1. This is the value of the function at f of x2, y1. That's at this point. And at this point here is the value of the function at f of x2, y2. And given is a 2D surface. So previously we were working in 1 dimension. So now we're in 2D. So you have this 2D surface. And based on the points you are giving and the value of the function at this point, when you are given an unknown value, like on this, if you look at this as a table, this blue rectangle, if you view it as a table and you are given the 4 corners of the table, you are given the 4 corners of the table and you are asked to get the value of the function at probably the center of the table, f of xi, yi. So that's bilinear interpolation. So you are now in 2D, and obviously things are much more complicated when you are in the 2 dimension. So you are going to use the Lagrange method to derive the method in 2D. So the first thing is that using the Lagrange method, you hold the value of y fixed and apply one-dimensional linear interpolation in the x direction. So this Lagrange form, if you look at the Lagrange form in 1 dimension, so you hold the value of the y fixed, then apply Lagrange form in the x direction to get equation 19 and equation 20. Then using these values of x1 and x2, you will interpolate along the y dimension to yield the final direction. So first of all, what we did is that we applied linear interpolation in the x direction, but keeping this y value constant, keeping this y value constant. So that's why y1 was constant here, y1 was constant here. Then we kept y2 constant, so y2 is constant here and y2 is constant here. Then using these 2 results, you'd interpolate along the y dimension to yield this final result here. Then when you substitute this equation and this equation into equation 21, you are going to arrive at this equation here. So simply put, this is the Lagrange form, but you are keeping y1 constant here. Then this is the Lagrange form. You are keeping y2 constant. Then here, you are keeping xi constant here. Then this is the Lagrange form. So substituting this and this into this equation, you arrive at this equation. So this is the for bilinear interpolation. When you have a 2D surface, this is the way to interpolate. So we'll go into an example to really understand it. So if you are given like a plate, a rectangular heated plate, then look at it as a table. The temperature at this corner of the table, at this edge of the table, is 60. The temperature at this other corner is 75.5. The temperature at the third corner of the table is 55 degrees. Then the temperature at the last corner is 70 degrees. Then based on this, you are asked to get the temperature at this point in the table, at this location in the table. Probably is at the center or just within the table, on the surface of the table. So based on this graph here, so here is the surface. We are giving this value, we are giving this value, we are giving this value, we are giving this value. Then you want to find the value of the function at any point on the surface of the table, because now we are in 2D. So we are simply going to use this formula here, equation 22. So putting all of this, so this value here is, this value here is simply f of x. This one here is simply this, is f of x1 comma x1, f of x1 comma y1. So that's this value. This one a is f of x2 comma, so this is f of x1 comma, so here is our x and here is our y. So here is x1 and here is y1. So this is x2 comma y1. Then this value here is, this value here is f of, this is f of x1 comma y2. Then the last point, the last corner we are giving is f of x2 comma x2. This is f of x2 comma x2. So these are the points you are giving. So if you look at it, x1, so I'm just writing the values here now. Okay. So x1, sorry about that. So x1 is simply y1 is simply equal to 1. Then x1 is equal to 2. Sorry, I'm not so used to this is, so I want to write x1. This is x1. There is, so this x1. X1 is equal to 2. Then y1 is equal to 1. Then x2, x2 is equal to 9. X2 is equal to 9. Then y2 is equal to 6. Is equal to 6 based on the question. So I hope you understand what I'm doing. So based on, this is the question you're giving. You're giving these 4 corners of the table and you're giving the temperature. So this is x1 and this is y1. So that's what I was writing. This is x1 and this is y1. This is x2 and this is y1. This is x1 and this is y2. Then this is x2 and this is y2. So this was what I was writing. So based on all of this, I'm substituting into this equation. So we know x1, we know x2, we know y1, we know y2. We know f of x1, y1. We know f of x2, y1. We know f of x1, y2. And we know f of x2, y2. So given this and substituting into the equation, we arrive at this particular value. So the temperature at this portion of the table given in the question is 61.2143. So based on interpolation. So these are the methods we are going to be considering for interpolation. So first of all, we started with 1D interpolation. So using a straight line, that's linear interpolation. Then using a second order polynomial, a third order polynomial, and using Newton's divided difference polynomials. Then we also talked about Lagrange polynomial, first order, second order, then third order, based on this equation here. Then based on this, so this is the equation. So once you know this equation, you can derive the formula for the first order, which we derived as this. So this is the Lagrange form polynomial, first order polynomial. This is the Lagrange second order polynomial, and this is the Lagrange third order polynomial. So you can see the trend. For third order, you need 3, 3, 3. There are 3 products. There are 3 products. There are 3 products. There are 3 products here. Then this is x0, x1, x2, and x3. So for second order, it's 2 products of x, 2 products of x. Then you just have x0, x1, and x2. So for fourth order, obviously there will be another product here, then plus f of x4. So that's just the general syntax. So now we are going to go into curve fitting using software packages. So there are, we've been doing the interpolation by hand using calculations. So you already know that MATLAB or Excel can do that for us. So we'll be talking about the software packages that we can use both for curve fitting and for linear interpolation. So we'll start with this method. So last week we talked about curve fitting and we did the hand calculation. So I just want to show you how Excel can just, you don't need to do all those calculations we're doing, even in Excel. Just putting your values, then Excel will we plot the graph, we plot the curve for you, the curve of best fit. Given these values here, x, y, we are asked to fit a logarithm model to it. So because of this logarithm model, so let me go to Excel. So I'm in Excel now. So this is the question. Let me just copy the question into a new sheet so that I will just start all over again. So this is the question, and I want to use Excel. We don't want to do all those calculations because last week we were able to fit a linear curve, a logarithm curve, and exponential curve, but we had to do some calculations, but which we don't want to do. We just want Excel to do it for us automatically. So we had to fit a logarithm curve to this. So in order to do that, we first of all plot it in Excel. So I just want to plot it first. So I'll choose a scatter, a XY scatter. So these are the points. Then we want to fit a logarithm curve. So when you want to fit a curve, all you do is to click on the points as I've clicked on it, then you right click, then you go to add thread line. So when you click on add thread line, you will see this box appearing. So since the question told us to fit a logarithm curve through the data, we choose logarithm. So if it was a linear curve that the question was asking us to fit, we'll choose linear. If it was an exponential, we'll choose exponential. But if it was a polynomial, we choose this. But in this question, is a logarithm curve, so we just choose it. Then obviously we'll get an equation. If to say we were doing it by hand, it was that equation we used to plot the curve. But this one is saying that the equation, you should display it on the chart. Then the R squared. Remember, we also calculated the R squared value. We did it by hand, which is the coefficient of determination. So once you've selected all the options you want, then you just click on close. Then Excel is going to automatically draw the line of best fit through the data, and is also going to show you the equation. So this is the equation of straight line, and this is the R squared, coefficient of determination 0.944. So remember I told you in the last class that you want this R squared value to be very, very close to 1. So if it's very close to 1, you know that the line is the best fit. And this is the equation of the line, this is the intercept, and this is the slope 0.9486, and this is a logarithm line we are fitting, so it's straight up in Excel. So like I said, if to say the question says that we should fit a logarithm line, so that's why we did that. If to say it was a linear, we just choose, if it was a linear line, we just choose linear. So that's the way to do it in Excel. So let me go back to the notes. So we have been able to do this. So in the notes, I explained the steps you follow just like I did. Then based on that, actually I chose, so based on that, you would draw the graph. So another tool Excel has is data analysis tool pack, so which you can use to do some analysis on your data. So in this question, we're given this set of data points here, and we want to fit this power model. So this is a power model, and we talked about it in the last class. So it's a non-linear model. So to linearize it, we need to you can, like I told you, you can linearize a non-linear model. So to linearize it, we'll just take the log of this equation that is highlighted. And to take the log, you just take the log of this. And the log of this is simply given by this expression here. So the log of this, so you have log. So there's supposed to be a log here. So it's given by this expression. Yeah. So if you do the log of all of this and you break it down, you would arrive at this equation here. And in the question, it says that the rho, this is sigma and this is rho. Theoretically, the value of sigma are rho are 0.5 and 0.667. That's when you fit a power model through this equation. And we want to confirm, we want to fit our data point with Excel and evaluate whether our regression estimates contradict the expected values for the model coefficients. So now in Excel, we want to, this is a non-linear model. So we linearize it by getting the log. And we want to get the coefficients of this, of alpha, rho, and sigma. And based on theoretical values, we're told that rho should be 0.5 and sigma should be 0.5 and rho should be 0.667. So we want to actually get these coefficients and want to confirm if these values are really correct using Excel. So since we've linearized, so let me go to Excel now and do it. So what I'm going to do is that this is the question given to us. Then we'll find the log of x, the log of r, and the log of u. So this is log of s. This is the log. Sorry, this is the log of x. This is the log of r, and this is the log of u. So we are going to do this. Then the aim is to get alpha, rho, sigma, and rho. So we could do it by hand. So this is actually multiple regression. We didn't do multiple regression, but it's kind of similar to linear regression. But in the textbook, I didn't do multiple regression last week, but in the textbook, they actually explained multiple regression. So you can just look at it. So this is multiple regression. The difference between multiple regression and linear regression is that in linear regression, this is y is equal to mx plus c. This is your linear regression. You want to get the slope and you want to get the intercept. But in multiple regression is simply y is equal to mx1. So let me just put m1 plus m2 x2 plus c. Sorry, I don't know how to use equation form to write in Google Docs. So this is linear regression. In linear regression, you just only have one value of x. But in multiple regression, you have x1, you have x2, you could even have x3, x4, x5. So that's like the difference between linear regression and multiple regression. So they are kind of similar, but obviously the equations you arrive at are very, very different. So this is a multiple regression problem because you have, this is your intercept because we linearize. So these are our intercepts given by C. But this is like our M1, and this is like our M2, and this is like our X1, and this is our X2. So it's kind of like a multiple regression problem. So we want to be able to find this slope and this slope, then this intercept. That's the what we want to do. But we want to use Excel now. And in the question, we're told that this sigma is 0.5 and this rho is 0.67. So we want to confirm using Excel to actually do it for us. So let me go to Excel, new share. So this is the question. So let me copy it so that I will start all over again. So let me copy it here. Yeah. So we linearized it by getting the log of x. So I'll put log of x on this column and say capital letter X. Then I'll put log of R here. Then I'll put log of U here because I want to linearize it. Then I'll take the log of X. So in Excel, to get the log of is the logarithm to base 10 a2. So I want to get the log of x, and here is a2. This is the log of x. Then I'll just drag it so that I don't keep typing the formula. Let's get the log of r. I'll drag it here. This is log of b2. Then I'll drag it down. And to get the log of u, drag it here. Then drag it down. So I've been able to get log of x, log of r, and log of u. So this log of x is our x1, log of r is our x2, then log of u is our y, is the output. So Excel has a feature called analysis toolpack that you can use to help us to do all of this. So when you, in order to get there, you go to data and you see data analysis. So in case you don't see data analysis on your Excel screen, so you just go to file, then options, then click on add-ins, then under Excel add-ins, make sure Excel add-ins is selected, then go. Then when you click this, make sure this analysis toolpack is selected. So once this analysis toolpack is selected, you are going to see it here on your screen. Okay. So once you've done that, then you just click on the data analysis toolpack. Then you go to regression. You look for regression. Say here is regression. Okay. So we are asked to put in our Y. So input Y range. This is our Y range. Our Y range is from F2 to F7. So I will simply put in F2 to F7 because that's our Y. Our Y is the output. That's from F2 to F7. So our X is from D2 to E7 because this is our X1 and this is our X2 because this is actually a multiple regression problem. So you have X1 and X2. In linear regression, it's just one X you have. But in multiple regression, you have X1 and X2. So your X range is from E2. So no, D2, sorry. It's from D2 to E7. So it's from D2 to E7 here. Then you make sure this new worksheet player is selected. Then you click on OK. Once you click on OK, Excel is going to generate another sheet for you. And that sheet is going to display your intercept and all the coefficients you are looking for, the standard error, all the statistical value, lower, the upper 95. So Excel is going to automatically generate this value for you. So this sheet, this is your intercept. Remember, we're supposed to calculate our intercept if we were using hand calculation. This is your slope because this is multiple regression and we have two x's. So this is the M1 slope and this is the M2 slope. And this is the Excel is generating a lower a confidence interval. So it's saying that for the x1 variable, which is sigma, we are 95% confident that it should be between 0.36 and 0.5. Then for the rho variable, we are 95% confident that is between 0.63 and 0.83. So this confirms the model. Remember in the question, it's saying that based on model calculation, the rho, which is x1, is 0.5. So this interval is within 0.5. So you are 95% confident that the sigma is between 0.36 and 0.5. So that means that the model results are correct. Then for the rho, you're 95% confident that the rho is between 0.63 and 0.83. And in the question, I think they got 0.8. So this is the way to do it in Excel. So Excel will automatically generate the R squared, the standard error, and the R value. It's going to automatically generate all these values for you. So that's the way to do it in Excel. And let me go back to the note. So now we have been able to solve this in Excel. So the last one in Excel. So I put in the steps to go through that in the notes. So this is the resulting line. So if you, when we're in Excel, we got the intercept as 1.522. We got the M1 as 0.423, and we got the M2 as 0.733. So let me go to Excel so that you can see for yourself. So in Excel, this is the intercept, 1.522. This is the M1 slope, and this is the M2 slope because this is a multiple regression problem. And so from these values, that's what I got in the question. And I was able to get this. So this is the linearized form. So to get the original form is a power model given by this equation here. So the original form is a power model given by this equation here. So this is the original model. So we had to first of all linearize it. So we got this. So in order to get the original model, you'll find the antilog of this. The antilog of this is 33.3. Then S raised to power 0.433, then R raised to power 0.733. So let's go to the last question in Excel so we are given this saturation growth rate model, and we are asked to determine these coefficients, K max and K. So this is a saturation growth rate model. And in the last class, I talked about it as being a non-linear model. And I told you that you can linearize it by getting the inverse. So this was like the equation I presented to you last week. And is a non-linear model, and you linearize it by getting the inverse. So when you apply the inverse, you're going to arrive at this formula. Then further simplification, you get this equation. So here is your y, here is your x. This is the intercept, and this is the slope. So when you plot 1 over y versus 1 over x, it's going to be linear. It will have a slope of beta divided by alpha and an intercept of 1 divided by alpha. So this model given to us is exactly the same thing as this. It's just that the coefficients are different. So if you apply the same linearization technique as in the first instance, and you break it down into this format, the plots of this as a function of this. So this is like 1 over y as a function of 1 over x is going to give you a slope of k divided by k max and an intercept of 1 divided by k max. So now you can use manual calculation to do it in order to find the intercept. After linearizing, you can just use, this is linear regression, it's not multiple regression. So we did this, and you use all those formulas that we derived and we used to calculate for the intercept and the slope. But we want to use Excel now to do it. So this is a case of linear regression. So the way we do it in in Excel is that we plot, we're giving f and k. So this is f, this is f, and this is k, and this is k. We're giving f and k. And the question, we want to get k max and k, because when we get k max and k, if you are to do it by hand, you get the slope and the intercept. The slope is k divided by k max, and the intercept is 1 divided by k max. So once you get this and this, you can get your k and your k max. So actually, we want to get our k and our k max. So in order to do it in Excel, since f is given to us in the question and k is given to us in the question, and we want to get our k max and capital letter K, all we're going to do now is to just choose a random variable for k max. So we put this k max in cell Q1. That's why I have Q1 here. This is cell Q1. Then this k is given to us. F is given to us. So F is on cell A2. F is on cell A2. Then the K. So we choose random values of K and K max, and we put it in cell Q1 and Q2. Then we use this equation to approximate the value of K. Then after that, we compare the K predicted, because this is actually our output. We compare the K predicted with the actual value of K we are looking for. Then after that, okay, I'm ending the meeting now. So you join me using the same